Okay, so here is a little algorithm that we are going to look at that has recursion. Now this algorithm, you can see it's called algorithm XX, and it accepts input an integer, say n, and then we have the recursive case when if n is greater than 1, then it does this little for loop 1 to 10, it prints I. For I equals 1 to 10, it prints I. And then outside of the for loop, it recurs, it calls itself, the input parameter is decreased by 1 unit. If we go further on, we can see the base case in the else part of this pseudocode, else if n is equal to 1. Then we have the base case where it just prints n. So if we examine this, if we do a little bit of a trace and a call graph on this algorithm, we can try running it for a small example. So we might have XX and we have the input of 3. We can see that it comes in there when n is equal to 3, it's going to do the recursive part of the conditional statement. It will print I 1 to 10, so it will do 10 printings, and then it will recur. So it will do 10 actions of printing, and then it recurs with XX, and the input parameter is now reduced by 1 to 2. It calls itself again. It goes to the recursive case because 2 is greater than 1. It does 10 prints, and then it recurs and it calls itself with 2 minus 1, which is 1. And now it comes back in. This time it falls into the base case and it just prints n, and that's just one action. So by just examining this, we might be able to see a bit of a pattern. It's actually done, I guess, approximately 21 actions, just by examining the call graph for a small example. If we want to be a bit more, mathematical about this, we can use a recurrence relation to describe the recursion. So to work out how many actions are done based on the input value n, if we look at this algorithm, we can see there are going to be 10 actions done right here, 10. And then it will recur, reducing the input by 1. So it will call itself and reduce the input by 1. We can also see what the base case is going to be. That is when n is equal to 1, it will do one action and it will just print. Okay, so we have this expression right here. So what are we going to do with that? We need to turn it into from a recurrence into a function of n. So we will do a little bit of algebra. We will telescope to the base case or unroll the recursion to the base case. To do that, we're just going to rearrange this expression, and to make it easier to unroll to the base case. So I've just rearranged algebraically that recurrence relation. And now it's t of n minus t of n minus 1 equals 10. Now I'm just going to unroll this to the base case, notionally, not completely. So you can see this is now showing all the recursive steps that it's going to do. N minus 2 minus n minus 3 equals 10, all the way to the base case, which will become, there's the base case, t of 1, and that's going to be equal to 10. Now, this is counting all the actions. This is a summation of all the actions. We're going to add all those together. To sum up all the actions, this is doing recursively, and when we do that, algebraically, we're going to cancel out the like and opposite sign terms, and we're left with an expression that is now a function of n minus t of 1 equals, and now we can see we've got 2 to n values of 10 on this right hand side of the equal, which is the same as n minus 1 tenths. So a little bit of algebra, just rearranging this. This is going to be equal to 10 n minus 1 plus t of 1, which is equal to 10 n minus 1 plus 1, because the base case is 1, which is equal to 10n minus 10 plus 1. That's equal to 10n minus 9. So what do you know? That's the number of actions. And let's see if it matches up with what we worked out earlier from our call graph. If we put 3 into this expression, we should get 21, I hope. So that's 3 times 10 is 30 minus 9 equals 21. That's really cool. That matches up. And because this expression is a polynomial linear expression, we can say the big O notation for this algorithm is big O of n. It has linear time complexity. And remember, this big O notation is a measure of how much work this algorithm does as n approaches infinity. It's asymptotic time complexity. Okay, so the next recursive algorithm we're going to look at is pretty similar to the first one we just looked at. There is one major difference though. You'll notice this one is algorithm YY. It does recur, but this time we've got the recurring case when n is greater than 1. We have a for loop that goes from 1 to n, and inside the for loop we have the recursion occurring. The else statement, when n is equal to 1, then that's the base case, and that's our algorithm. So we have a recurring case and a base case. So this algorithm, if we try and work out what it's doing, let's try doing a call graph for it. So we can call it YY and let n equal to 4 to begin with, and you'll see when it comes in here that n is going to be greater than 1, and we are going to do 4 recursive calls of YY, and then the n input value will become 3. So there will be 4 calls, and we will get YY3, calling with YY3. Now I'm giving myself plenty of room here. You'll soon see why. I'm trying to spread out my tree. So now each one of these YY3s will come in recur and call them 3 times with YY2. Now 2 is the input parameter this time. So each one of those will do 3 calls to YY2, etc. 3 calls. Okay, when we have YY2, each one of those recursive calls will do 2 calls to YY1. So each one of those will do 2 calls to YY1. That is a whole lot of work. Now YY1, of course, is the base case where the recursion stops. So this call graph is getting very, very wide at the leaf node level, extremely wide. So let's have a look at this algorithm and see if we can work out its time complexity and approximately count how many actions it's doing. So like before, we'll set up a recurrence relation to try and work out how many actions are happening. This time we see there are n recursive calls, and each recursive call is reducing the input by 1 unit. And then if we look at the base case here, that happens when n is equal to 1 and 1 action is done. Let's tidy up this graph here to get it out of the way. So 1 action is done. So let's have a look at this expression here and think about an algebraic method we could use to turn it from a recurrence relation into a function of n. I don't think the telescoping will work very well here. I think this one is more suited to substitution. So if you can see, we're going to just substitute that to the base case or for a few times and try and get an idea of the pattern. So that is going to become n times n minus 1, and just substituting that in, that would become that. Okay, and now we're going to do more substitution. So this time we will get, this will be equal to n minus 1, n minus 2, t of n minus 3. That is keeping on going. So we can see if we keep on going, we're going to eventually get to n minus 1, n minus 2, n minus 3, dot, 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 maybe to 1 times t of 1. And that is equal to n factorial t of 1. Now t of 1 we said was equal to 1, so this is going to be approximately n factorial actions done by this algorithm YY, which makes it big O notation n factorial, which is factorial time complexity as n approaches infinity. So that's really, really bad. That's a lot of work. Okay, so those algorithms we just looked at, XX with the recursion outside of the for loop that we determined was linear time complexity, and the YY with the recursion occurring inside the for loop that we've found to be factorial time complexity. We can play around with these in any coding language. I've put them here in SnapApp's Edgy, which you can take a screenshot here and try them yourself. See it here, instead of doing the printing inside the for loop, I'll just try to do something a little bit different. I'm going to, in SnapApp's Edgy, just add a node, randomly selecting its label to be a value between 1 and 5,000, just to make it a little bit more interesting. So to be able to do that, adding a node, we do need to create a graph structure when we're calling this function, and then we can pass in that input parameter. Similarly, for the recursive algorithm with the recursion inside the for loop, done something similar. I'm adding a node here with a label chosen randomly between 1 and 5,000. And to be able to use a graph, I need to create the graph first in SnapApp's Edgy and then call this YY function. So let's see that running. So I just need to open up SnapApp's Edgy. Here's the first algorithm, XX. This is the one that has the linear time complexity because the recursion, as we worked out earlier, is happening outside the for loop. So, and you can see the nodes are going to be randomly labeled as they're created with a value between 1 and 5,000. So let's just try running that with a input value of 4. So let's just run that on the stage, very quick. That's done. Now let's just increment that by 1 and see what happens. Run it again. Done, very quick. Because of the linear growth of the time complexity, it doesn't make a big impact as we increase the input size. Let's try it with a value of 6. Okay, it has returned. Okay, let's try it one more time with a value of 7. There it is. Not too bad. Okay, the number of nodes, 27. Okay, now we're going to try, so we've tried that one. Let's try the other one that has the factorial time complexity. Let's have a look at that. Before we do, I just need to advise you to be able to run this one. You need to set the maximum amount of nodes in our SnapApp's Edgy to be the maximum possible value, which is 1,000. And you do that from that little settings button there. So I don't want to go for 6 first up. I just want to go make the input be n equals 4 to begin with. Let's try that one. So there it goes. It's got the recursion this time inside the for loop. How many nodes do we end up with? 40. Okay, I'm going to increase the input size now just by 1 from 4 to 5 and try running this again. Okay, so let's have a look. Now this one is it's got factorial time complexity growth, so it's doing a lot more work when we increase the input by 1 unit. So you can see how many extra nodes it has to add, and then the base case being reached so many more times. Okay, let's just try it with the next biggest number. Let's go from 5 to 6 and see how it goes. Let's try that again. Here we go. You can see every time it hits the base case, it says hello for a brief amount of time. This time we have n is equal to 6 as our input. And here we go. You can fast forward this bit if it's a little bit tedious for you. It's going. Hello, hello, hello. Well, it's still going. It's got a lot of work to do. It's quite fascinating, but as I said, you could fast forward this bit. I'm patiently waiting to see when it finishes. If it finishes. Still going. Still going. That's a lot of nodes. I don't know how many. It's springing up from everywhere. That was just ink. Oh, there we go. So, Edgy has reached the maximum amount of nodes it can show. And that pretty much demonstrates the impact of having an algorithm with factorial time complexity and an increasing the input size. Pretty fatal. So pseudocode in SnapApps Edgy. You could also try it in Python. Here is some code that I have created for this algorithm. You can see XX here. I have to pass in the graph input parameter here for it to create a graph correctly. And there's my value of n. It's pretty much matching up the pseudocode quite closely. I have the recursive case. In the recursive case, instead of printing, I have the for loop adding a node with a label that's randomly selected between 1 and 5,000. And then outside the for loop, there is a decrease and conquer recursive call, just like there is in the pseudocode. Now we know this one is linear. If we look at the one that has factorial time complexity, you'll see it's pretty similar, except this time the recursive call is inside the for loop. If we look at the whole algorithm created in Python Trinket, coded in Python Trinket, we need to include a few libraries for this to work. We need to create a graph, and then we can call those functions, and we can plot them out and see what they look like. So let's try that right now. I've got that all ready to go in Python Trinket. I've been playing around with it already, as you can see. At the moment, I've got XX uncommented, which is the linear one. Let's try it with just 10. N is equal to 10 as the input size. Let's try that. Let's see how it goes. Should be pretty quick, I think, with linear time complexity. That's not too bad. Let's just triple that to n is equal to 30. And let's see how it goes. Oh yeah, still reasonable. Let's just make it triple again to 90. Oh, wow. Okay, that's quite a lot, but it was not reasonable time. Let's comment XX out, and let's uncomment YY so we can run that one. The one with the factorial time complexity. I won't run it with 6 to begin with. I'll run it with 4. And let's see how we go with that one. Not too bad. Let's increase it to 5. Now we're not doubling or anything this time, just increasing by 1. Let's see the impact we have by just going from 4 to 1. Okay, that wasn't too bad. Let's go to 6. It's doing a lot more work. It's got factorial time complexity, therefore doing a lot more work. Okay, oh, that is looking really dense now. Let's try going to 10. Just 106. Let's try 10 and see how long that takes. Okay. That's taking a while. You can see the impact, the factorial time complexity as the input size is growing. We have to wait a lot longer to get a result. I'm hoping it'll come up soon. We can fast forward this bit. There we go. Wow. Thanks for watching.